MA prime. Because VO prime is equal to 0, and that follows that A is equal to A prime, right? This is A, and this is A prime. So if you are on the ground, and your friend is in the bus, and if the bus traveling with constant velocity, and you and your friend observe rock dropping whatever down, for instance, with acceleration g, you both will agree that the rock is traveling with acceleration g. But if your friend is in the rocket that accelerates upward, they will disagree with you. For them, rock will drop with different acceleration. So that frame is not inertial. So what I just showed that if frame travels with constant velocity, it is also inertial. So if frame of reference travels with v of frame equals to constant, then it is inertial frame of reference. Does that make sense? Let me call this 21. And 22, oops, I can say that if S prime and S are inertial, both, then A prime means that A and A prime are exactly same. And then what follows from here? If this is same as that, then this should be 0, right? From here follows that velocity of frame, okay, derivative is 0, and that means that velocity of frame is constant. I proved reverse theorem. So here we proved that if frame of reference is traveling with constant velocity, it is also inertial frame. And here we show that if frame S prime is inertial, then it travels with constant velocity relative to any inertial frame of reference. Is it clear? So now we got full set of inertial frames. If you know that one of frames is inertial, everything that travels with constant velocity is also inertial. Yeah.
For 22, what does that first line say?
If S and S prime are inertial frames, yep, which means that we don't see difference in accelerations, we act with the same force and we see result is the same, accelerations are the same. That can only happen if this term is equal to 0. What does it mean that this term is equal to 0? It means that frame is traveling with constant velocity. Does that make sense? I should say here that this vision of Newton's laws became possible only for Newton, who built calculus. Before he built calculus, really smart people like Aristotle, people laugh at him when they think about Aristotle's physics, but he was not less smart, even maybe smarter than Newton. But there was no yet time to develop corresponding math. And math opened our eyes, and boom, immediately discovery of calculus led to discovery of laws. And first knock, from my perspective, was done by Galilei. And Galilei introduced also something amazing that later Einstein used. It is a thought experiment. Thought experiment. Einstein called it Gedanken experiment because his first language was German, and thought experiment is Gedanken experiment. Now people following Einstein, everybody use this word. Look, really distinctive feature of Newtonian dynamics from Aristotle's dynamics. Aristotle's statement was, to move something you need force. But Newton's, to accelerate something you need force. Two different things, right? Today we could say, oh, easy. If force causes velocity, that's first order differential equation. Immediately the basketball example, let me that one initial condition is enough. Look at this basketball shoot from the same point with two different initial velocity. Doesn't go the same way, so Aristotle is wrong, right? Another consequence is that if force is equal to 0, it does not mean that object stops, right? Aristotle would say it will stop, no force, no motion. Newton says no force, no acceleration. Means that if you had initial velocity, you will stay that way. And first person who realized that was Galilei. It seems like such a big deal, but you know, he discovered acceleration. People never thought that rate of change can also change. I mean, today it feels like, how could people not realize that? They didn't. And today even economists who are not the most advanced mathematicians, they use derivatives and second derivatives. Actually, some mathematicians even do some kind of advancement in economics and get Nobel Prize in economics, because mathematicians cannot get Nobel Prize, but if you are mathematicians who discover something for economics, then you can. Whatever, so let me show you what Galilei did. He did really beautiful Gedanken experiment. He said, imagine I have inclined plane. An inclined plane was his particle accelerator, where he was getting lots of discoveries. So if I send object with velocity in 3 different settings, everybody quickly agrees that if you shoot object uphill, it will slow down. If you start motion down the hill, it will accelerate. Galilei said logically, if you shoot object on horizontal, it should not accelerate or decelerate. It should go with the same speed. This is how Galilei, who did not have air hockey, no any kind of low friction devices, it was old time. So he developed law of inertia. So the law of inertia, or now Newton's first law, it was discovered by Galilei just logically. Just logically, which is pretty amazing. Interesting. I'm already on item 23. According to my notes, it is item 3, I think. No, because I allowed myself to navigate it unpredicted way to make it more interesting. Hopefully I didn't confuse you. I mean, my method is give you a little more, but emphasize core that you definitely need to understand. We don't need functional spaces right now. In quantum mechanics, where you will enjoy functional spaces. Actually, in CS33, we will learn guitar string oscillation. And that will be Fourier series, which is serious example of functional space. So we'll be there at the end of this academic year. But idea that Newton's second law is differential equation of second order, that is idea that without proof of theory of differential equations, I want you to take from this lecture. Inertial frames I did. Yeah, I had some examples. I don't know. Yeah, I think your brain still works, right? Yeah? It's not burning, no smoke out of ears. Okay. Yeah, no smoke. Okay, just mild. All right. Actually, I will do some maybe problems just for entertaining. Not just entertaining, for learning, please. Let me solve super simple problem that actually I remember myself being puzzled by this problem, because you know sometimes when the problem is simple and this is first ever problem you solve, you might be surprised. then we have two boxes, M and big M. And let's say you push these boxes with constant force F, horizontal, there is no friction. And the question is, how do they push each other? We know with the same equal and opposite forces, that's Newton's third law. But what is that force? Yeah?
Well, the first thing you do is you realize they have the same acceleration. And so you can use Newton's second law to find the acceleration. And then so now that you know the acceleration and the mass of the boxes, you know the force on both of them.
Amazing. That is exactly what I will do. Thanks. If you see that they travel like one single object, right? Like Gabriel said, with the same acceleration, let me go even further. Say, I don't see that they are actually two objects. I look at this, it looks like one single, right? Then you could say that F equals ma. All right. Now, is this force exerted on this object? This is kind of counterintuitive. You have a question?
No. No,
It is counterintuitive. Many people think, sure, because of this force it travels. But right answer, no, it doesn't travel just immediate reason why big M is traveling is because little m is pushing big M, right? So, until we will learn what is field, gravitational field, or, gravitational field actually helps us to, okay, let me tell you this way. Only objects that are in direct contact interact with each other, act on each other. So if I push this part of the table, I only push this part of the table. The other part of the table is pushed by neighbor parts of the table. If table is not solid and I push here myself or my weight, that side will stay there, right? But if I push sand here, sand on that side will not move, right? Because it's not connected. Forces like gravity and electromagnetic force, they pretend they act on distance. But then if you introduce concept of field, everything again becomes contacting, right? So you are attracted by Earth even if you are not standing on Earth, right? Why? Because Earth creates field and you really are in touch with gravitational field. So therefore that moves you. Forget about that, we will be there. So what moves this object? That object. So therefore immediately we can say that since this object is pushed by little m, big M also exerts force on little m. Make sense? So if I write Newton's second law for big M, what that will be? Let me call this force F1. This is negative F1, but if I don't put vector and just notate absolute value, then just F1 is good enough. The only force exerted on big M is F1. And that force is equal to big M multiplied by acceleration. From these two equations, I can say that acceleration is equal to F over M plus M sub here. You see that F1 is equal to Fm over M plus M. That's the force of interaction. And you guys see interesting thing that may be also counterintuitive. What if I push not from this side but with exactly the same force from that side? Will these two affect each other with this, act on each other with the same force?
No.
Yeah, it says immediately big M. So if you push on small m, the numerator contains big M. If I switch, they will switch. It's kind of strange, but this is true. That's what equations tell us. Any questions here? Is this all clear? All right. Let me see, we have 4 more minutes. Let me see in 4 minutes what else I can tell you. I don't think I have anything specific I want to tell necessarily right now. So let me tell you one more thing. Last thing here. Today, yeah. So, I really won't make it super nice, but let me do it. Yeah, I think it's enough. If we have same 2 objects but connected with the rope, no, of course, if I just push this with force F, it will not work out because rope will lose, right? So let me push it this way, F. So why does this move? Because they are connected. So therefore, due to this connection, there is force. Let me call it tension force. And let me call this tension force T1 and T2. Do you guys think T1 and T2, which one is bigger, smaller, or equal?
Is the rope massless?
Guys, will those answer? Don't say that. Yeah. Okay, these 2 forces are equal. Are they equal because of Newton's first law, because of Newton's second law, or because Newton's third law?
Second.
Yeah, I would expect that most of people who did not solve this problem will say third law, but answer is second law, and apparently Morgan is right. Mass of the rope matters. And I have enough time to answer this question. Let me look at the rope. What is T2? T2 is the force rope exerts on big M. What is opposite and equal? Force that what exerts on what?
Big exert on.
Exactly. If this force is rope on block, then block on rope is Newton's third law pair. So this is negative T2. Let me put vectors here, then this will be negative T2. Same thing here. This is negative T1. Make sense? And then I can write Newton's second law. Because why these 2 forces are not related by third law? Because this is rope on little m, and this is rope on big M. Newton's third law says 1 on 2 is same as 2 on 1. And this is 1 on 2, and this is 1 on 3. Oops! Why these forces are equal? Not really. But if you write Newton's second law, then you will see that negative T1 plus negative T2 is equal to mass of the rope times acceleration. And only under condition that rope is massless, we see that T1 is equal to negative T2. They are opposite and equal. But if rope has mass and it moves with acceleration, then these 2 forces are not equal. The difference is ma. That's the last point. I will ask you for Thursday lecture, think about, first of all, any questions. I will be happy to start with any questions, particularly ropes, because ropes will be a big part of next lecture. All right, let me stop.